Everybody, welcome to video notes 10.2. So we're going to use equilibrium and shifting in equilibrium conditions to describe what would happen. Okay, it's called LeChateliers principle. Okay, so read section 17.7, do a couple self-checks, and you can get bonus on the quiz. All right, so let's talk about what equilibrium is again. When you first start a chemical reaction, you have all reactants most of the time. Those reactants are going to react and turn into products. As soon as products start to form, they can start colliding and turn back into reactants. Okay, so all reactants to products, some products turn back into reactants, and then so that's the shift back that way. Then you get to a point where no matter what, the number of reactants stays constant and the number of products stays constant. And so we have what's called an equilibrium constant. Okay. So it's reached equilibrium when it looks like the amounts aren't changing, but we know these collide, boom, turn back into that, but then these collide, boom, turn back into that, so it's at equilibrium. Okay. The LeChatelier's principle states that when you change an equilibrium system, you cause it stress, and then the equilibrium system shifts to relieve the stress and to get back to K. Get back to K. Right? So let's look back here. This is equilibrium, so we need these amounts at equilibrium. If we stress out the equilibrium system, it's got to get back to this constant. Okay, so what kind of stresses can we do? So here's 4 ways that we can change an equilibrium system to cause it stress. Okay. Adding a substance. That's one of the ways, like adding or removing a substance. So if you add something that's already in the equilibrium system, you're going to stress out the side that the substance you added is on in the equilibrium system. So you're going to increase the rate of that side of the reaction, and so the equilibrium will shift away from what you add to get back to K. To get back to K. So K is a constant, right? So to get back to K, it would have to shift so that it could keep that ratio of products over reactants constant. Products over reactants. This is generic. Remember, there's coefficients, all that good stuff. But here's the constant. If you add more products into the system, then those products are going to collide, turn into reactants to get back to that ratio of products to reactants. Okay? What if you remove one of the substances in the equilibrium system? Well, then that side of the equilibrium system won't have anything to react with, so it's going to slow down, so it's going to shift towards the whole or towards what you removed. Okay? Pressure. How does pressure affect an equilibrium system? Well, it only affects gases. Pressure only affects gases. So don't worry about solids, and don't worry about liquids, and don't worry about aqueous. All right? When we talk about pressure, you got to look for gas particles. So if you increase the pressure in an equilibrium system, it's going to stress out the side with more gas particles, so it's going to shift to the side with less. Oppositely, if you decrease the pressure, like if you've given it more room to spread out, it's going to shift to the side with more gases. Okay. So how do we change pressure? Well, usually we can change the size of the container. So if the pressure increases, how do you do that? Well, then you have to decrease the volume of the container. Right? If pressure decreases, it's because the volume of the container gets bigger. So remember these things, and we'll talk about them as we go. How do you change the temperature of a system? Well, you have to add or take away heat. So we're going to treat heat as a reactant or product. So we have a reactant plus heat turns into a product. That's endothermic, right? Or a reactant turns into a product plus heat. That's exothermic. That's endo, that's exo. Then treat it like what it is. So if we add, so we have this reaction in equilibrium. If we add more heat, it's going to stress out this side and shift away. Okay. Here, if we add more heat, it's going to stress out this side and shift away. Right? So it's like adding or removing a substance, except that substance is going to be heat. Okay. And so that's how you got to treat heat. All right. So here's a chemical reaction. Woo! It's an equilibrium reaction. So we could write a K expression for it. And we have to do products. NO to the 4th power times H2O to the 6th power. Who's writing so small? Can you even read that? I can't, but tell me what it is. NH3 to the 4th power times O2 to the 5th power. And I could include them all because they're all gases. Where does the heat go? The heat goes on this side because it's negative. Okay. What if we increase the pressure on this equilibrium system? Okay. we're going to stress out the equilibrium system on the side with more gases. So 10 gas particles, 4 plus 5, 9 gas particles. Increasing pressure stresses the product side because there's more gas particles. So then the equilibrium system will shift left, toward, shift left, I'll put shift left toward reactant to get back to K, to reach. All right, what if we increase the temperature? Well, increases the temperature will stress products. Why? Because the heat's on the product side. Okay, so if we increase the temperature, this side will start reacting faster because that's the side with the heat. So it'll shift left toward reactants to get back to K. Get back to K. Okay. What if we increase the concentration of ammonia and oxygen? Well, here's ammonia and here's oxygen. If all of a sudden we dump more ammonia and oxygen into the container, then this side will speed up and stress out and push towards the products. Okay, so stresses reactants and shift right or product. So you would increase the rate of this reaction by adding more. So it's going to form more products to get to that concentrate. Decreasing the amount of oxygen. So we're going here and we're taking some of that out. Okay, so then stresses reactants. And so it'll shift toward reactants because missing O2. Right. So if you're missing something, then this reaction can't occur at the same rate it was occurring at. So this reaction keeps going at the same rate, and it shifts this way so that it can get back to the same rate. Increased concentration of nitrogen monoxide in water. So put more of this in. So then this side of the reaction starts to go faster. Faster reaction on right shifts left. Okay, so there's a lot of ways to think about it. You can think about which side is going to react faster, and so it's going to shift away from that side. You could think about which side is going to react slower, and it'll shift toward the side that's going slower. Okay. All right, so you got to think about it in a lot of ways, and we can do this. So here's another reaction that says negative 92, so we have 92 kilojoules over here. Okay. We'll do the pressure, increase in pressure. So let's count. We have 2. Pressure only affects gas. Gas. Okay. Make container bigger is volume. Right. So that's gas again. So some of these are gas related. Right. So on this side, the product side, we have 2 gas particles. Here we have 4. Okay. So if we increase pressure, this side will react faster because they're smushing 4 particles together. They're going to hit more often. So the effect on the reaction stresses reactants to react faster. All right. So then it's going to shift in position of equilibrium toward products. Okay. So reason, higher pressure affects more gas. All right. Make the container bigger. That means give this container a lot of room to spread out. Okay. So effect on the reaction. It's going to stress more reactants. Reactants again. Okay, so it's going to shift toward product, which is saying it's going right, toward product or toward the right reason. Bigger container means more volume, means less pressure, so goes away from less gas. That's why it's going, All right, so back it up, Harbin. I'm going to take you through this again because I messed up here a little bit, but hey, I'm owning it. Bigger volume means a bigger container. Bigger container means less pressure. So then this side can't react as fast because it has so much more space. So it's going to shift toward the side with more gas particles. Okay. So the increased volume means the pressure goes down. So it goes away from gas towards less particles. Okay. Increase in temperature. It's going to affect the side with heat on it because the temperature goes up. This side stresses out, and this side's going to react faster. Effect on reaction. Stresses products. Shift in equilibrium position toward reactants. And then it's going to, the reason it's going to do that goes away from added substance, and that added substance was heat. Right. So when you talk about pressure, relieving pressure helps the side with less. Okay, adding pressure helps the side with helps this releases pressure on the side with more. Okay. Increased concentration means adding more nitrogen and hydrogen. So this rate's gonna go faster and shift away. Okay. We'll talk about these two in class. I'm gonna leave them blank and then we'll talk about them in class. Okay. What the heck does a catalyst do? Okay, so we had an exothermic reaction and we could have an endothermic reaction. All right, so this is reversible and this is reversible. A catalyst lowers the energy barrier, right, so that there's a lower hill. But the hill's lower for both forward and reverse reaction. So does it speed up forward or reverse reaction or both? It's both because reactants turn into products or reactants turn into products or vice versa, products turn back. But when you lower the hill, it decreases the rate of both reactions. So equilibrium is achieved quicker, more quickly, but it doesn't affect the constant. Okay, so let's put it all together. So here's a chemical reaction. We need to write an equilibrium constant expression. So we take the product, CO2 and CO2. So this is a solid, so it's just CO2 over reactants, and that's solid. So we're done. Okay, so predict the shift if more carbon dioxide is added. So we add more of this, it's going to shift away from CO2. Predict what happens if we add more calcium oxide. So here's calcium oxide. If we add more of this is a solid, so no change. Predict the shift if the volumes increase. Volumes increase gives us much more space, so it's going to shift toward CO2. Give it more space to spread out. Okay. How do you remove something in a chemical reaction? You can't reach in and pull something out. So if a substance that's not part of the equilibrium reaction is added and causes one of the equilibrium substances to have a side reaction, is really removing it from the equilibrium system. Okay, so here's an equilibrium system. If we add aqueous NO, sodium phosphate, it's not part of this reaction at all. So what is it going to do? Well, the phosphate ions will react with the iron ions because we have a PO4 -3 and an iron +3, so they're going to precipitate, make a solid. Okay, so this phosphate ions will be like, hey, iron, come with me. So it's removing the iron from the equilibrium system. So it's going to shift left. Okay. So you can remove something in the equilibrium system by using another chemical side reaction. Okay. Here's an equilibrium system that we're going to study in class, but notice this is cold. And so temperature decreased. And which way did it shift? It shifted towards pink. So heat must have been on this side because when heat was removed, it shifted towards pink. Right? Here's a couple other reactions we'll explore in class. Or graphically, how does it look? Okay, so here's equilibrium, right? You got products, right here, NH3, product, and reactants, and here's their amount, right, at equilibrium. Okay. All of a sudden, N2 was added right here. You can see that spikes. That means N2 was added. So let's see what happens to the concentrations. N2 was added. As N2 is added, H2 goes down. Why? Because N2 and H2 react, right? Shift this way. And then NH3 goes up, right? Because N2 and H2 are reacting and making more NH3. Okay. Then notice they get back to equilibrium. Okay. But there's different amounts, but the ratio stays the same. Okay. Products over reactants is constant. Right. Constant. It was constant here. A change was made, and then the equilibrium shifted to get back to the same constant. Okay. So, to review, LeChatelier's principle says that if you stress the system, it'll shift to relieve stress. Adding stuff always shifts away from what you add. Removing stuff shifts toward what you add, what you remove, sorry. Pressure goes up, shifts from more gas to less. Pressure goes down, goes towards more gas. Volume is related to pressure, related. So make sure you know how those are related. Heat, treat like a substance, so up here, that's what heat does, those same kind of things. Catalyst speeds up both reactions, so it doesn't change the final ratio. Okay. Don't forget to do what Moltato's doing. Self-check from the book. All right. Here's our objectives again. Peace out.